please.
Okay. Thanks for inviting me, or I guess I invited myself by showing up at your seminar for a few weeks and then responding to Yulia's call for upcoming speakers.
That's the right way to go.
Yes. For a little bit.
Very nice of you.
Yeah. Thank you. So for a little bit about me, you can see my video up in the camera here. This is also what I looked like a couple years ago. I'm an assistant professor of computational media at UC Santa Cruz. We have a computer science department, but I'm not in it. I'm still in our School of Engineering, but I'm in this small department that broke away from computer science a couple years ago to do things that are relevant to the arts and social sciences and lots of other things. Often the applications end up being focused on, well, the students like it when the applications are focused on video games, but we think of the much broader category of computational media. I've been using ASP since I had to go look through my email for when the first emails that I sent to other people being excited about it. Apparently it was around 2008. I was at a, it was like a workshop on the automation of the scientific process or something like that. And Oliver Ray, who I think maybe some of you know, was giving it. Oliver Ray.
Yeah.
He was using, I can't remember the name of his system, but he said, I'm using this thing called answer set programming, which I thought was a silly name. And after the talk, I said, can you say more about what that answer set programming thing is? He said, it's amazing. It's like Prolog, except actually declarative. And I thought, wow, what would cause somebody to say something like that? I'm really interested. And at the time I looked around for stuff about ASP and I found LParse and S models, those trusty old tools. I've since switched to the Patasco tools, Klingo and Clasp and so on. Most of my applications with ASP focus on helping people design interactive media, usually for video games. So this might be generating puzzles, generating the rules, generating character descriptions, or maybe fictional narratives like the story in games. It also comes down to things that you might more recognize as formal methods for verification, such as making sure a puzzle can't be solved in ways that are undesirable. I have a little slide about that later. But I think one of the things that's been most rewarding for me is just participating in random discussions on the Patasco users mailing list, where I found somebody wanted to use ASP to generate a playlist for their electronic music show, and they wanted to select tracks that went after each other nicely. There's higher profile applications on software package management with the SPAC company, multi-robot pathfinding. So there's been a bunch of times where code that I wrote in response to a mailing list question ended up in a figure in somebody's paper at AAAI a few years later. And that feels really satisfying. I feel like I'm being part of collaborating in this community where I can write 3 lines, and that was just the 3 lines that they needed to get their encoding of something to go from n cubed to n squared, and suddenly it satisfies their needs. So as I suggested, I really like helping people with performance optimization, like keeping the meaning of their program constant while knocking a few numbers off the exponent from n to the 4th to n log n or something like that. Those are really satisfying times. I try to get more people to do automated testing, which is part of what this talk is about. I've done a bunch of applications where you deploy ASP on a web server, on a mobile device, or in the browser of a mobile device. And so I've got some wisdom in that area, and I'm not the best at it, but I do really enjoy helping people work through saturation encodings to get this beyond NP expressiveness out of ASP. Those are fun logic puzzles with implications for the real world when you help people do it for an application. So in several of my applications, there's this notion of quantifying over play, quantifying in the sense of universal quantification. This happens all the time when we're making things meant to be used in an interactive context. So on the left is a figure from one of my older papers where we were generating content for a mathematics education game, where we wanted to make sure that there were educational things like students will see that a laser split into half and then added back together produces the same value that it was started with. But it also had aesthetic properties like symmetry, spacing, and balance. But the trouble is that when you give that puzzle design to millions of middle school kids using this educational game, they find alternative solutions that don't do the math, that completely bypass the aesthetic properties. So we want this property that when I give somebody a puzzle, the design features that I thought I put in there should be inescapable, in the sense that solving the puzzle implies that it satisfies whatever predicate I wanted. So it could be that it's got those mathematical and aesthetic properties in it. We want those things to be inescapable side effects of the solution. And we don't want this just to apply in our simplified logical model of the game. We want our logical model of the game to be 100% faithful to the pre-existing educational game that we're trying to generate content for. So beyond just verifying properties of the model, we want those to imply properties about the real game. So there's this concern for like, how do I make sure my real world thing matches my ASP formulation? In an application that I've been informally consulting with this company called Lightforge Games, they want to generate. This is like, I don't even know if I have permission to share this screenshot. This is a screenshot from their in development game where they want to generate very detailed worlds. And you can imagine the basis of those worlds is mostly just laying down two-dimensional bounding boxes on a grid. And the grid is actually not very large. So it was reasonable for me to offer to help them with ASP on this process. The logical properties of interest in this domain are like, are two bounding boxes touching? Are they overlapping? Is this one allowed to be nested inside of that one or not? Those are sort of like the lowest level concerns, like the purely geometric things, but they would like to be writing constraints about high level things, like it will take players about 15 minutes to traverse this map. As they go through this dungeon, they will face, 3 fights and collect this amount of treasure or something like that. Those are the higher level player experience properties we would like to constrain, but we have to get the geometry handled before we can even start writing rules to simulate those things. So to abstract from this real world application, one of the things I'm modeling, I help them make a little file, geometry.lp, at least that's how I name my ASP files. You can kind of think of this as a n-dimensional qualitative spatial reasoning engine. For this game developer I'm working with, I just call it a collision engine, a physics engine, because that's what they're familiar with game development. So there's this idea of, I want to be able to model bounding boxes, like there's a box B, there's a box C, and they're not overlapping, but they are touching. There's a point P and Q, and P better be inside of B, and Q is not. So the way I express that is with the front end of my qualitative spatial reasoning engine, I write facts like, we're in a two-dimensional world, and the axes are called X and Y. The coordinates can range from 0 to 128, or maybe 127. There's points in boxes, P's and Q's, B's and C's. I'm interested if the geometric property point in box PB holds. You have to specify the properties you want to check so that it doesn't, at ground time, consider all possible properties it could check between all pairs of geometric objects. You can say, I'm curious if this point holds, and I want to reject the design if it's not the case that point P is inside of box B. So that's what the game developers write when they're making their world generator. Behind the scenes, inside of geometry.lp, there's a bunch of low-level rules that actually give the implementation of these point in box or box touching box constraints. And you can imagine there's a choice between, well, how do I even represent the idea that the X position of P is at location 3 in one encoding that we call the one-hot encoding? Maybe it's the most intuitive, simple one. You say, it is true that P on axis X is at location 3. Really simple to write rules that depend on it. But you can imagine this leads to performance problems when suddenly somebody says, I want my world to be 10,000 wide. And now if I want to check if 2 points are touching, I have to check that perhaps all over this 10,000 by 10,000 grid. It's better to represent these things for efficiency reasons in binary. If I want to say px is at position 3, I can say, oh, to be at position 3, you need to have your least significant bit set and your index 1 bit set. So this is sort of representing that 3 in binary. This way of writing the rules is more tedious and harder to debug, but it scales to things. So it's not that there's one of these that's the right answer. The one-hot encoding, easy to read and write. When you get answers coming out in the command line, you can kind of mentally visualize them because it just directly says X is at location 3. You don't have to think about the bits of it. So there's good and bad. We're not going to decide to just do one of these or the other one. We actually want to maintain both versions of the library and keep them in sync with each other. So when we add a new high-level constraint, it's supported by both of the reasoning engines, the one that's good for development and testing and the one that's good for high efficiency deployment. So this leaves us with this question of like, what's going to give us the discipline to keep these two implementations in sync with each other? Do we just say, hey, a grad student should always check it? They should manually run a bunch of tests to check if they're different. Who keeps track of all these tests? Who maintains that set of tests? Well, even just running tests is itself a pretty tedious thing. Maybe some automation can help with this. So conveniently, there is already a large literature on this topic of unit testing and test automation, of which there's actually very little overlap with that and ASP, even though we've had multiple workshops on software engineering of ASP. Some of the important concepts is this idea of a test case. You can kind of think of this as a problem instance attached with a label that says, I think this problem instance should be satisfiable. I think it should be unsat, or if it's an optimization problem, I think it should be optimal with a certain score. And a suite is a collection of test cases that might be hierarchically nested. Like if you have a very complex answer set program, you might have tests that only test. You can imagine in my n-dimensional geometry engine, I've got tests that refer only to points. I've got tests that refer only to boxes, and I've got another set of tests that assumes the correctness of points and boxes in the way it tests point-box interaction. No, that's not how it works. Points are built out of boxes. So it's like, I want the point test to pass before I bother running the box level test, because that's a higher level concept built on top. So there's this idea of like, what is a software unit? I guess in ASP, we use the word module roughly to describe like one of these LP files that has some rules. It might depend on predicates provided by an upstream module. It might expose predicates that are going to be used to another one, but I'm usually testing my answer set program at the level of a single LP file at a time. And a realistic application might have 20 of these files that depend on each other directly or indirectly. So once you have these concepts, one thing you can do is you can run your tests during development. Like every time you make a change to one of your LP files, one of your units or one of your modules, you might rerun all of your tests to see, did I fix the bug I was trying to fix, or did I introduce a bug that only shows up in an application of one of my modules? If you want to, you can even do test-driven development where you write your tests first as a way of saying, well, I want a problem encoding that would be sat on this instance and be unsat on that one, but I don't have the encoding yet. You can write the tests ahead of time and then see those tests go from failing to passing as you implement more of it. That's pretty satisfying, but not everyone likes that style of development. So as I suggested, I'm not the person who invented unit test automation. For almost every major real world used for applications language, there are many testing frameworks. I do a lot of Python programming, so I often use the unit test library for Python. And regardless of whether you can read and write Python, you can roughly see that there is a class that is a subclass of test case. Like somebody provides this kit for doing testing, you make a subclass of it with a bunch of methods that all start with the word test. And then some logic behind the scenes knows how to find every class that is a subclass of test case, find every method that has test in the name, and run those one after another one. The idea is that you don't actually have to write a loop over these things. Just by clever naming of your test code, the test runner knows how to run your tests. Sometimes it will allow you to like filter only to the tests in a certain suite of test cases, and it will give you nice at least in the terminal, nice ASCII art tables of which tests were passing, which ones are failing. Also metrics like how long did each one take, so you can find out your slowest running tests. If you were in the command line, you might run python-m unit test, and then whatever module you're trying to test. So that's the workflow for Python unit testing. I have something that I call ants unit in a reference to many of the other testing frameworks are called. There's one for C++ called CPP unit, or there's one for Java called JUnit. So mine was ants unit to fit in with that naming scheme. So here's a screenshot of a part of the unit test suite for that geometry or geometry binary, my two versions of that geometry engine. You can specify that a bunch of your different test cases, and I have two of them down here, share some test code. So I might say, okay, all my tests are going to run in a one-dimensional world that only goes from 0 to 10. It doesn't have to be a realistic test case. It can be a very microscopic one-dimensional with only two values test. And then you write the individual rules or facts that you need for a problem instance, such as in the tests that refer to the point axis relation test, there is a subtest, because you can have tests within tests. There's a subtest that tests the equal case, the LT for less than case. And I might say there's a geopoint P, P's X must be equal to 3, and also reject if not geo holds P was X equals to 3. Implicitly, you don't have to write expect sat with these. If you're just making test cases where satisfiable is the expected case, you can leave that off. But you can imagine there's a declaration you can sprinkle in here to say expect unsat or expect optimal. So this was, and this, the overall syntax of this file with like indented chunks, pieces like chunks that are, there's a colon and an indented piece inside of it. This is following YAML syntax, which is an existing data language that I didn't invent. I'm just sort of using that data language. It's roughly equivalent to XML, but less verbose in the syntax of it. So I've got chunks of ASP inside of, think of it as like hierarchical collections. And there are certain conventions, like anything that is a test must start with the word test with a capital T, and that's how the test runner knows how to go find all the tests in this file. I guess there's a few other keywords in my test language, like the word definitions, which lets you give short names to your modules or make groups of them for testing very large files. We'll see much more of this stuff like this, but assuming you have all of your various LP files you want to test and one big test.yaml file, on the command line, you say ants unit test.yaml, and then maybe you say only run tests in a certain category like point axis relations. So you might have 50 tests, but there's only 20 of them you want to run while you're working on a bug fix for that one module. This came from a case where there's two different qualitative spatial reasoning engines, and I want to make sure that they agree with each other. I don't demonstrate it here, but there's an easy way to swap out one of the modules and run the same set of tests across two different implementations to make sure that they have the same behavior on those handcrafted test cases. But even so, this geometry.lp is like 500 lines. It's not a particularly big and complex program with hierarchical nesting of things. In a previous application that I did when I was a consultant, for complicated reasons, we were making a symbolic execution engine for the ARMv7a instruction set. Like we had a bunch of machine code and we wanted to symbolically execute it to find out which inputs would cause certain lines in the machine code to be reached. And we implemented this in ASP for reasons that I won't get into. But you can imagine inside of this very large and complicated thing that needs to basically have a CPU design in it with a bunch of logic gates, there's a really basic predicate that says that models like what value is present on any wire inside of my hardware design over time. So I might say the signal at time t on wire W at bit B was value 0 or 1. So I can model like a single wire in this large CPU design was either 0 or 1, or it can actually model the idea that it's unknown, that it's not known to be 0 or known to be 1. So that was one of the key predicates in that application. RTL device, this stands for register transfer level. There was a way of instantiating little hardware chunks that connected to each other via wires. Predicates for that were, I think you would say that there was a device whose name was instance that had a certain configuration and it connected to certain wires in this larger thing. So this larger program, I think it was maybe 1,500 lines of code total, almost all the hardware design stuff, was mostly only involving just these two predicates, like what are the devices and what do those devices imply about signals over time? So as an example of this, you can imagine deep inside of a processor design, there is an AND gate and somebody needs to implement an AND gate. So I'm going to say, here's a rule that lets you derive that the AND gate has an output 1 if the inputs are 1 and there was a device that was an AND gate that connected those ins to those outs. So I've got a bunch of rules like this to make AND and OR gates, a bunch more rules to make adders and ALUs and register cores and CPU cores and so on, building up many different layers. But it's all relating signals to the presence of devices or relating large devices to the presence of their subcomponents, like deriving the details of a hardware design from the instantiation of a larger one. I guess this was a slightly more realistic rule that said, if somebody is trying to instantiate an ARM processor device, I need to instantiate a multiplexer that has its wires connected in a certain way. So deep inside of the hardware design, it says, if you want the whole processor, you definitely need this thing that does something with the memory data register that I don't remember because it's been a few years. But importantly, it's all about taking the instance that they requested and deriving the presence of a component inside of it from it with a certain configuration. Roughly, this rule is of the form, if you ask for the large device, that implies, like deductively implies, the existence of the small device inside of it. So it's a rule that where RTL device depends on RTL device. I say that this is a big application, not necessarily because it has a large number of lines of code, but that it leads to when a problem instance gets to the solver, it might involve 10 million variables that I don't have easy ways to shrink it smaller. So it leads to usefully large problem instances at the solver level. So the next few slides have a few screenshots from the test case for that hardware design thing. The individual tests that I wrote were actually extremely small things that often only had a single fact inside of each one. So when I'm testing the AND, OR, and EQ individual logic gates, I just say, okay, when you're instantiating an AND device, it better output this bit string, but there's a little bit of helper code that is shared between all of my tests for those small little logic gates. The idea is to take as much of your test code that is shared between tests and factor it out so your individual tests are as small and as simple to audit as possible. So like I've got const A and const B that have all possible bit patterns, and mentally I can type out the correct answer for these different expected things. Oh, did somebody want to say something? Okay. So I'm testing like an AND gate that is 4 bits wide, that takes in 4 bits or 2 sets of 4 bits and outputs 1. So that was like one of the super low level tests. But you can zoom out to say, well, I want to have a test that says 1 + 1 + 1 is 1 with 1 carrying out. I'm testing the property of a single bit adder here by instantiating little test inputs and writing that there is a device here, expect cout, expect the carry out bit to be equal to the bit 1. So that's testing an adder. Zooming out further, I might say that when somebody, when somebody instantiates a 4-bit ALU, an arithmetic logic unit that does all the computation inside of a core, that when you, what does this one test? Like when you add things, it should set the various zero and carry and other bits expected. I don't want to get into the hardware design of it, but this is sort of zooming out in scales to test larger and larger modules. Eventually, you get to a point where we have a CPU that can not only decode and execute instructions, it can keep that state over time. So I had a test, on line 1200 of my test suite that says, test software multiply. I wrote a small C program to do multiplication a tedious way just to exercise things like loops and conditionals. I compiled that to machine code and then copy and pasted the machine code into my test case to say, here is a 50 instruction long program. And now I want to test simple things like 3 times 5 is 15. So when I actually go to write the 3 times 5 equals 15 test, all I'm writing is A was 3, B was 5, and the expected result was 15. And implicitly expected to be satisfiable. Like it better be consistent with having those bits of the number 15 as output. What's important is that I can actually, because I've abstracted out the helper code for this test, I can make many, many more multiply tests without ever running my C program again. I can think of it as inject new test inputs very easily by 2 or 3 lines of test code. So all of my tests, if you remove their helper code, are about 1 to 3 lines. 1 to 10 lines long or something like that. But in the end, I have a large suite of tests that test everything down from like, what is the meaning of a bit on a wire, all the way up to, can this compiled machine code run? Importantly, I can express that instead of saying the input was 3, I can attach a device that models the idea that it's unknown, and I can have the solver solve for a number that when multiplied by 5 equals 15. And because of overflow and so on, there's actually more than one answer, but that's why I don't do that much. But you can think of it as all the normal things you would expect from ASP, and such as the ability to like reason forwards and backwards from outputs to inputs. Those now all apply to this model of machine code executing over time. And it turns out that I have almost as many lines of test code as I do of code implementing the processor. It's about 1,300 lines of both. And this pattern where I have equal or more test code to the thing being tested is common in my experience with both my test framework, as well as when I've worked at companies like Google and Microsoft. We write, for whatever application code we're writing, we write about that much or more test code to go with it to build assurance that we've implemented the right thing that's going to behave the right way. So it's nice to see that that pattern kind of generalizes to ASP. Let's see. I think in some of the teaching material for ASP, we teach people this idea of, how do you organize your code? Well, we use this generate define test pattern of put your choice rules at the top, put your deductive rules or your normal rules in the middle, and then your integrity constraints at the end. That works for programs out about to 100 lines. But when you start refactoring your program into hierarchical modules that depend on and provide predicates to the other one, this way of organizing your code breaks down. And then there isn't very much advice written on how to do large scale ASP stuff. But I found that forcing yourself to write tests ends up accidentally giving you good software design. Think about it in terms of reusability. Because your modules are used in multiple tests, you're already exercising their reusability a little bit. It kind of tricks you into better software engineering when you have those tests along the way. And further, it leads to this weird thing that even in this very, very large program, I only have 2 choice rules and 2 integrity constraints. Everything else is just deductive rules that instantiates objects that have expectations about those bits. So it's when I'm writing almost all the code, I'm not even really thinking about choices and non-determinism. It's almost all entirely deductive rules, P if Q type things. And so I'll skip some of the details of that. The reason to do that is that we often want our tests to run very quickly. I don't want to wait for the grounder to ground for 15 minutes only to let the solver run for 15 minutes before it says sat. I try to give it extremely small test instances that have no non-determinism at all. If there was a choice rule in my program, I factor that part out into a module, and then I don't use it, and I just hard code the facts that I want it to consider so that almost all of my tests are completely resolved by the grounder in a few milliseconds rather than a long grounding and solving time. And when I do have tests that are slower, I will do things like put them in a separate slow test suite that I don't often run, or I might put the word slow in the name so that when I'm running my tests, I can say run all tests except for those containing the word slow in their name, which lets me get quick feedback on did I break everything, and only if the preliminary tests pass do I bother to run the more heavyweight full system things. And a result of running your program all the time over and over is that you become more sensitive to what makes it go fast or slow. You get a better sense of how to write performant ANS prolog. Whereas if you're only working with a few test instances, you often don't run them enough to ever develop that sense of what is high performance code. Yeah, so there's unexpected benefits of testing. It's not just about the correctness of your code. You often get better quality code that's more readable, more nicely organized. Secondarily, you get documentation in the sense that people can look at your test suite and understand, what is this module supposed to do? Well, however it's implemented, it makes these three things be sat and these two things be unsat. It functions as a sort of tricking you into documenting what your modules are. And on top of it, it makes you very conscious of performance, which speeds you up in the future because all of your development is faster and not waiting for the grounder and solver. So how do you get this and use it in projects with your students? If they're literate in Python, they just pip install Ansunit. And then there's some trouble that I haven't updated the library in a few years, and I don't know if it works on the current version of Python or not. So there might be some source code changes that are needed, but I did bother to make it as easy as pip install Ansunit. And there's a chance, depending on which version of Python, it'll work directly. And I put in my plan, like if time permits, we actually went longer than I thought. Maybe I'll switch to questions that all of you have rather than just showing you a bunch of command line stuff. So that's it. That's it for the slides.
Thank you so much, Adam. So it's question time to everyone.
Adam, thank you for the interesting talk. Let me first say how I understand your approach to testing. Tell me if this is wrong or incomplete. So you have a piece of code that you want to test.
Yes.
And every test consists of a context, some additional rules that you add to the piece that you are testing, plus information what you expect. Do you expect this problem to have an answer set or not, whether it's going to be satisfiable or not? And so when you are debugging a file, you have this list of collection of tests, and whenever you expect that maybe with a few rules modified, maybe now your code will perform correctly on all tests.
Yes.
You say go, and then it runs all tests and it tells you whether everything is as you expected, right? That's pretty much how it works, right?
That's right. Or more likely, things don't go as expected, and it tells you which one of your tests failed. Yeah.
Okay, that's nice. I was thinking at first when you started that asking whether your program has a stable model where it's satisfiable is not very informative, because what you want to find out is whether the stable model that it produces is exactly what you want, but then realize that you can do this by adding appropriate constraints.
Yeah, exactly. So like if you want to test, A implies B, okay, B if A is true, become unsat if not B. So you can your main program may just contain rules like this, but your test code often contains a constraint that will say, if it misbehaved, become unsat. And that's how you can, with a little bit of extra code, when I was testing before I had test automation, I would often read the output answer set programs extremely carefully to be like, does it have the properties that I want? And I realized I should just write more rules to detect the properties I want and then say it's unsat if it doesn't have that property. So it requires a little bit of a different way of thinking. But it's a way of doing the bulk testing without ever reading the results.
Yeah, so in other words, detailed information about what you expect to happen, you don't put it into this expect part, but rather you put it in a list of constraints, including
exactly.
That's
so,
very nice.
so the only things you can expect are sat, unsat, and optimal in my setup. And you have to, using those primitives, you express all of your application concerns as more constraints. But realistically, it is very useful to see the actual answer sets that come out because sometimes your test is wrong. So there's a way of running, there's a bunch of different command line arguments you can pass to the test runner. And one of them is like -O, show the output, so that even when the test passes, you can actually inspect the answer set and make sure it matches your expectation. And one common form of testing that I do is I run the solver once on my program, and if that answer set looks good, I then use that answer set to make a test to make sure that answer set stays good in the future. So basically anything that the solver would have chosen via choice rules, I now just write those down as facts of like, that's what was chosen, and I still want it to be satisfiable. But often I get those facts by having the test runner show me the outputs, I inspect it, and if I like it, I think of it, sometimes they call it the golden data or the expected data. Like, even though it's non-deterministic, something that used to be a model should still be a model again. It's not a proof that the program is equivalent to what it was before, but it's a point of evidence that a solution that used to be valid is still valid now.
Okay, thank you. And one other thing I wanted to ask you about at the very beginning, I think on your second slide, there was a formula that I didn't quite understand. Can you go back?
Yeah,
yes,
I think it was this one. So I can try to read this one in English.
Yeah, so say it in English. What does it say?
Yeah, there's two predicates of interest. Solve says, does solution S, think of it as a solution is an arrangement of pieces on the board. In this game, the player is supposed to put these light blue pieces around such that lasers split and free cute animals trapped in space. So one predicate says, like, does their solution indeed solve a given puzzle? And don't think of this as ASP. S is not really a variable seen by grounding. This is my abstract formalization of it. The ASP code looks different. The other predicate is concept. Think of this as just whatever visual properties I wanted the solution to have, such as laser passed through a divider. Laser, yeah, that might be one. Like, I want to make sure that people use this puzzle piece in my solution. So I want it to be, there exists a reference solution and a puzzle, because I want to generate a puzzle, or in this application, my goal was to generate puzzles that were provably solvable. So they come with a certificate of solvability, like a reference solution. So produce a solver and a certificate solution such that for all alternative arrangements, if the alternative arrangement T solves the puzzle, that implied that the concept was also satisfied. And I have a paper here that explains it in more detail. The important thing was that it was a exists for all style thing. So I could not solve this synthesis problem with a SAT solver, because this problem is, if you think of concept as just being some arbitrary predicate phi, that's polynomial time checkable. This problem is outside of NP, assuming P not equal NP. So this is something where I really made use of the full expressiveness of ASP to express things on the second level of the polynomial hierarchy.
Okay, thank you. That answers all my questions. Thank you.
Okay, and it was actually this particular application with the educational puzzle generation that prompted me to make the test automation framework, because there was this need that the logical model must agree with the pre-existing software. No divergence is acceptable. Or if there was a divergence, they just wouldn't use my generator. That's the equivalent.
Adam, I have two questions. One is with respect, so when a test is, you say, okay, run those tests, will it run the test specification on top of the overall program, or you were referring to something as modules, or it actually, depending on the kind of test was asked, like it will like grab some modules and only.
Yeah, so there's a declaration in this language. One of the keywords is the word modules. So you can say all geometry tests inside of this like nested thing depend on the modules called geometry and example world, where geometry was defined to be coming from a certain file name. And example world wasn't in a file anywhere. It was just a small bit of inline code. So it's not that it automatically knows which modules are needed. You have to declare ideally just the smallest subset that makes your test run as quickly and as fast as possible.
Okay, so in this regard, your tests is you can gear them towards specific submodules, so towards specific parts of your code. And having said that, you also refer to some software engineering aspects, which, and obviously, classically there is no such thing as a module. Like it's just a blob. And
yeah,
I think so. Was it a file, like basically a collection of files where you whenever?
Yeah, the reason I put unit in quotes here is like, I know this is not a logical word. This is me using the software engineering term of unit from unit testing and saying, what is a unit for ASP? For me, it seemed to be a single LP file, along with some discipline of how to arrange those ASP files or the .lp files. So in my mind, a module is an LP file is a unit, but that's just a convention I have from doing all my applications. It's entirely possible, of course, to put it all in one giant file, which makes it hard to make tests that run quickly because everything gets considered in every test.
And basically, when you were referring, so okay, if you have 100 lines of code, you still have this choice rules and normal rules and finally integrity constraints. But basically, that's not what's happening in applications you've illustrated here for majority of was this one. So that would actually, this application would be modeled by, I don't know, 100 files, say, or some.
Oh, it's like 10 files, I think.
10 files each.
Well, I modeled it after, like there was an existing, like I didn't invent a CPU design from scratch. There was an existing design that was in Verilog, and I made a sort of analogous piece. Whenever the Verilog program had defined a module, I put a couple hardware modules into one LP file if they were related, like all the parts of the ALU fit in one thing, all the AND and OR gates fit in one separate file. So there's a lot of subjectivity in terms of when do you group things into different modules. And I found that one way to resolve that subjectivity is to say, well, I should organize my files in a way that the tests run quickest. And that gives you a way of preferring some organizations over other ones because some of them are easier to test than others. But one of the larger things that I found is that as applications get more and more complex, I still sort of have roughly a constant number of constraints and choice rules. It's the number of normal rules that is the thing that grows with complexity proportional to what's in the domain. But that's just my particular style of using it. Other people might write things in a different way.
I guess what you call a unit is a just meaningful subset of rules. Meaningful in the sense that you know what you expect from it when you run it in various contexts.
Exactly. And in particular, it's often the case that, let me go back to, there was a previous slide where I was talking about the representation of binary numbers. Oh, sorry, it's not there. It's the signal one. In my test suite, I actually have a couple of different ways of representing signals. Like the way that scales to the full complexity of the processor design is the one that models individual bits. I have another representation where I can just say, at time t, wire contains a specific number like 5 or 13 or something like that. And some of my tests run with this simplified format. But you might think of like, well, how do you swap out this low-level thing upon which everything else depends? The idea is that I have different modules that expose the same, think of it as the same API or the same set of customer-facing predicates, but its internal implementation is different. And some of my tests use the slower, easier to read one. I think that was represented here, like one hot versus binary. Sometimes there is a low-level design choice, and you kind of want to make it so that almost all the rules in your program are agnostic to the fundamental thing of like, how do I represent a truth value on a wire? In hardware engineering, sometimes they'll do simulations that actually model an unknown state of a wire. So a wire is not just 0 or 1, it could be in a explicitly unknown state, and that complicates things. So I have most of my tests not use the version that has an explicit unknown state because it just adds complexity. So yeah, I make modules out of things that are easy to test together in a group, trying to, anytime that module depends on another one, I tend not to include that other module. I just provide facts that would have been derived by that other module.
Adam, was my understanding correct that when you were saying that you actually want to have a code that can be tested agnostically, that was actually in one of your illustration, you had this extra code just compiled within the tests themselves that would be added everywhere. So that could account, like here, multiply codes, that this part would actually be responsible for some kind of conversions from one type of input to another type of input. Or not quite.
Well, I say there's not many tests that I have that have big chunks of machine code in them. It's only the highest level tests that test the processor executing across many clock cycles. I think there's only 2 such programs like this in my larger test suite. But even then, I don't have one block of machine code per test. You can kind of see in here, it says definitions, multiply code, and then there's this big block of yellow stuff. That was like think of it as like an inline string that's not in an LP file anywhere. It's just concatenated onto these small bits of facts like A was 3, B was 5, result was 15. So this big block of yellow test code, plus these small little facts, plus the modules I depend on, are together what forms a specific test instance called 3 times 5 is 15.
Any more questions?